expressions from truth table. So here's an example. Let's say A, B has these inputs. Okay, so that's the output and A, B are the inputs. The question is, write a Boolean expression for Y. Now, you could potentially guess that, is it an OR gate? It looks like an OR gate from the first two, but then the third one, the third line is not right. 1 plus 0 is not 0, right? It can't be an AND gate because then the second one is violated. So it's not a simple gate. It's something more. It's more complicated. You have to mix different gates in order to come up with an expression. So I'm going to show you two methods to do this. Okay, there are two methods. And the reason I'm going to use two methods is because you want to try both methods, and whichever method gives you the minimum number of gates or minimum number of ICs, whichever is your constraint, you can use that constraint to use the expression. But there are two ways to do this. So the first method is what I would call the sum of products. Okay, what we'll do is we will write something like Y equals, so it's a sum of products. So there'll be a product and then you sum it. So something like this. Okay, so in order to write an expression which looks like this, you need to use this logic. I'll write it down next, and then we'll just use that logic to solve the problem. Okay, first, find rows where output is 1. Second is form products of inputs such that you get the required output. The required output here being 1 from there. And I explain what this means. And then finally, sum all expressions into. Okay, let's see how this is applied to the example I showed you. We have A, B, 0, 0. Zero, 1, 1, 0, 1, 1, then 0, 1, 0, 0. Okay, so step number 1, find rows where the output is 1. Okay, the output is 1. This will be row 2, right? Y equals 1, A equals 0, B equals 1. The second step is form products of inputs so that you get the required output. Okay, what it means is you need to form products of A and B so that you get Y equals 1. So when you get Y equals 1, A would be, you'll have to complement A and then take the product with B. So this is step number 2. You try to find what values of A and B when taken multiplied will give you Y equals 1. for this particular row, right? So A complement will be 1 and then B1, and you multiply them, you'll get. And the third step is to sum them up. Now there is, in this case, there's only one row which is 1. So there's nothing to sum. But if there was another row which was 1, then you could have another expression and then you sum them up. So this is the final expression. There's nothing to simplify. Now you may ask, is this good enough? This is based on your specification. Do you have access to one inverter and one AND gate? If you do, then you can build the sum. What's an example of product of sum? So what you do is you take products. We'll take products of sum. So sum would be something like this. Okay, so that's the idea. Now, here is the algorithm. 1, find the rows with zeros. Now, earlier we found rows with 1s, but here you find rows with zeros. Next, form the sum of inputs such that you get the required output. And it's a similar thing like before. I'll show you how this is done. Don't get intimidated by that. And the last thing you want to do is take the product of all Boolean expressions into. Okay, that's it. So let's just apply this on this problem. So we had A, B, and Y. 0, 0, 0, 0, 1, 0, sorry, 1. 1, 0, 0, 1, 1, 1. Okay, first find the rows with zeros. So there are 3 rows with zeros. This is 0. So that would be row 1, row 3, and row 4. Okay, for row 1, we have y equals 0, A equals 0, B equals 0. For row 3, we have y equals 0, A equals 1, B equals 0. Row 4, we have y equals 0, A equals 0, B equals 0. Sorry, this should be 1, 1. So this one, and 0, 0, 1, 0, 1, 1. Okay. Step 2. Okay, let's form the product. Let's form it right below this. So we need to write a sum with A and B such that we get the required output. So here the required output is 0, and we need to sum these such that we get y equals 0. And the simplest way to do that is to write A plus B. So 0 plus 0 is 0, and so we wrote that. Let's do it here. If you write A plus B here, you get 1 plus 0 is 1. You don't want that. You want something plus something, that's something with A, something with B, plus gives you y equals 0. As you can see that the way to do this is to do A complement plus B. So when you have A complement, 1 will become 0, and when you add it to 0, you get 0. And then for this one, I'm just writing it like this so that you don't confuse it with an AND. Okay, now we have y equals 0, A equals 1, B equals 1. So you need to take the complement and then add it, and you get y equals 0. So this is my step 2, and then final step 3. is to take the product of the sum. So the output is going to be A plus B dot with A plus B dot A complement plus B complement. This is your answer. Okay, now clearly this expression is fairly complicated. It requires 3 OR gates, and it requires 2 AND gates. But then you also have to factor that you need to take complements of A and B. So you require 3 NOT gates. So that's a lot of expressions. You could try to simplify this. And my guess is that if you simplify it, you might end up with the same expression I wrote down previously. But you could also do this thing, which is instead of taking that, just live with this. Just use this expression as your final answer and build your circuit based on that. Now, what people do normally is if you are given these 2 methods, the smart way of using these methods is you find from here see how many rows have zeros, how many rows have ones. In this case, we note that there's 1, 1, and there are 3 zeros. So because there's only a single 1, you want to use this method, sum of products. You don't want to use product of sum. However, if you see a different problem, there are more number of ones and less number of zeros, you'll use the other method, which is the product of sums. So it just depends on what output you have, and you'll use it based on that. If you have 2 ones, 2 zeros, then you probably are better off using either expression.